In the name of God. My name is Amir Hossein Vahidi, and in this video, I will present the topic, the effect of acid attacks on the mechanical behavior of concrete containing Forta-Ferro fibers and microsilica. To begin, let me briefly outline the structure of this research. In the first step, we will discuss the introduction and problem statement. The next step covers the fundamental concepts along with a review of related studies. Then, in the third step, we will go through the experimental program. In the most important part of this research, we will analyze the experimental results. Finally, in the last section, we will present the conclusions and provide suggestions for future studies. Chapter 1: Introduction and Problem Definition. Concrete is the most widely used construction material. However, by nature, it performs poorly when exposed to acid attacks. In today's world, the expansion of industries has led to an increase in pollutants, causing the acidification of water, soil, and air. This phenomenon results in acid rain, which poses a serious threat to both ecosystems and structures. When acid rain comes into contact with concrete structures, it reacts with the compounds in cement, leading to porosity, cracking, and a reduction in the durability of the concrete. These effects bring about several consequences: reduction in the service life of structures, increased CO2 emissions due to the need for additional cement production, decreased structural safety, pollution of water and soil resources. There are several strategies to improve this situation. One solution is the use of modern materials. Another approach is the use of pozzolans such as microsilica, nanosilica, or fly ash, and a further method is the use of fibers to enhance the ductility of concrete sections, such as steel fibers and glass fibers. In this research, microsilica was selected as the pozzolan and Forta-Ferro fibers were chosen as the reinforcement because Forta-Ferro fibers demonstrate good resistance in corrosive and alkaline environments. It should be mentioned that sufficient explanations are already available in the slides, and in order to avoid making this video too lengthy, the content is presented here briefly and in summary form, while additional details can be found in the slides. Three main hypotheses were considered in this research. The first hypothesis is that microsilica increases the compressive, impact, and electrical resistance of concrete. The second hypothesis is that Forta-Ferro fibers improve the tensile and electrical resistance of concrete. The third hypothesis is that acid attacks reduce the mechanical properties of concrete. Accordingly, three main objectives were defined. The first objective was to investigate acid attacks and the compressive, tensile, impact, and electrical resistance of concrete containing microsilica and Forta-Ferro fibers. The second objective was to monitor the physical changes in the concrete specimens, including weight, height, and diameter. Finally, the third objective was to provide a comprehensive picture of the behavior of modified concrete, in order to determine whether the combination of pozzolans and fibers can be effective, useful, and beneficial. In Chapter 2, we focus on the fundamental concepts and the research background. First, we start with the basics of fiber-reinforced concrete. Concrete without fibers is referred to as plain concrete. The fibers can be steel, glass, carbon, or other types. The role of fibers is essentially to absorb energy and increase resistance to cracking. As shown in this figure, a force applied to a beam causes cracks in the tensile zone of the beam. If the beam is reinforced with fibers, these fibers can prevent crack propagation or at least significantly delay the formation of cracks. Like any other material, fiber-reinforced concrete has certain advantages and disadvantages. The main advantages include increased tensile and flexural strength and control over crack widths. On the other hand, its disadvantages include higher production costs, especially when using steel fibers, as well as reduced workability and flowability of fresh concrete. Regarding applications, fiber-reinforced concrete is used in industrial structures, flooring, tunnel construction, shotcrete, precast elements, road and airport pavements, hydraulic and marine structures, and some specialized applications, with additional details provided in the slide. The types of fibers in concrete, as mentioned earlier, include natural fibers, glass fibers, metallic fibers, synthetic, man-made fibers, and hybrid fibers. Moving on to pozzolans, these are silico-alumina materials that initially have no binding properties but react with calcium oxide produced by cement hydration. Pozzolanic materials are categorized into natural and artificial types. Their advantages include increasing compressive strength, reducing cement consumption and consequently CO2 emissions, decreasing permeability, and enhancing bonding between the cement paste and aggregates. Fresh concrete also has specific properties. It should maintain a plastic and workable state and not yet be hardened. Three main characteristics are assessed: workability, segregation, and bleeding. Factors such as water-to-cement ratio, aggregate grading, and curing temperature influence these properties. In hardened concrete, characteristics such as compressive strength, stress, strain behavior, tensile strength, and modulus of elasticity are important. In this study, we focus specifically on compressive and tensile strengths. The first article was by Mr. Kalali and his colleagues, which examined the cracking behavior and failure process of concrete reinforced with Forta-Ferro and polypropylene fibers under uniaxial compressive loading. They also evaluated several parameters, such as stiffness index, compressive strength, and others. The most important finding was that the strength and deformation of concretes containing Forta-Ferro fibers were higher than those containing polypropylene fibers. The graphs from these experiments are also shown in this section. The next article was conducted by Mr. Dashti and Nemetsada. They investigated the mechanical behavior of concrete containing Forta-Ferro fibers and calcium aluminate cement, CAC, under sulfuric acid attack. In the mixed design, fibers were used at three volumetric ratios, 0%, 0.4%, and 0.7%, and another mixed design involved replacing 100% of CAC with Portland cement. The key finding was that a 0.4% fiber content could enhance compressive and tensile strength, and full replacement of CAC with Portland cement increased strength by up to 70%. Overall, the acidic environment led to a reduction in compressive strength by up to 30% and tensile strength by up to 20%. The next study was conducted by Nemetsada and Fala. They focused on high-strength concrete reinforced with Forta-Ferro fibers exposed to sulfuric acid attack. The main finding was that the presence of fibers helped control local cracking and prevented sudden failure. Another study by Nemetsada and colleagues examined concrete reinforced with Forta-Ferro fibers and compacted nylon aggregates. Both the fiber content and aggregate replacement ratio were varied. The key results indicated that 0.5% fiber content increased compressive strength by up to 15%, tensile strength by 25%, and flexural strength by 30%. Additionally, the nylon aggregates reduced permeability and water absorption. Moving on to the pozzolanic materials studies, the first article was by Mr. Jean and colleagues, who investigated the effects of microsilica on concrete properties. The results showed that replacing up to 30% of cement by weight with microsilica positively influenced concrete strength. A limitation noted was that high microsilica content increased initial and final setting times by approximately 1.5 times. The graphs from these experiments are also presented in this section. The next study was conducted by Mr. Hosseini and colleagues. They replaced 10% of cement with microsilica and evaluated concrete performance in sulfuric and nitric acid. Results indicated that compressive strength in ordinary concrete decreased by 20% under acidic exposure, whereas in microsilica-containing concrete, the reduction was limited to 12 to 15%. Tensile strength decreased by 15% in ordinary concrete but only about 10% in concrete with microsilica. Overall, microsilica enhanced durability and reduced permeability in corrosive environments. Subsequent research by Mr. Hassan Cathcoda and colleagues examined the effects of microsilica and a waterproofing agent against phosphorus iodide. Results showed that microsilica alone increased tensile strength by up to 15%, while the waterproofing agent alone reduced permeability and improved durability. The combined use of both materials increased compressive strength by up to 20% and provided optimal performance. Finally, Mr. Cantor G and colleagues studied the effects of styrene-butadiene latex powder, nanosilica, and microsilica on concrete strength in acidic environments over 90 to 180 days. They found that styrene-butadiene latex powder reduced permeability against acid, and both nanosilica and microsilica densified the structure and enhanced durability. The graphs from these experiments are also presented in this section. Chapter 3, Laboratory Programs. In this chapter, our aim is to investigate the mechanical and physical properties of concrete containing Forta-Ferro fibers and microsilica. The structure of this chapter is organized such that first the materials used are introduced, then the mix designs are explained, followed by the sample preparation procedures, and finally, the tests performed on both fresh and hardened concrete are presented. Materials used. The materials used include Portland cement, coarse aggregate, fine sand, water, Forta-Ferro fibers, microsilica, and superplasticizer. Additional details are provided in the corresponding slide. Aggregate grading. The aggregate grading was carried out according to ASTM standards, and the grading curve, as shown, is included in the standard text. Mix designs. The mixes were prepared with a fixed water-to-cement ratio of 0.48. The table includes 9 mix designs. The number for microsilica shows its percentage by weight. The number for Forta-Ferro fibers shows their volumetric percentage. For example, the sample M7.5F0.4 contains 7.5% microsilica by weight and 0.4% Forta-Ferro fibers by volume. Sample preparation. Cylindrical samples were prepared for compressive strength, tensile strength, electrical tests, and dimensional change observation. The dimensions were 200 mm in height and 100 mm in diameter. For particle testing, samples were made with 150 mm in diameter and 65 mm in height. Mixing procedure. The mixing was done as follows. First, coarse aggregate, sand, and Forta-Ferro fibers were mixed for 1 minute. Then, cement and microsilica were added. Finally, water and superplasticizer were added. After mixing, the samples were prepared for the slump test. After hardening, the other tests were conducted. Testing conditions: the tests were performed under 3 conditions. First, the non-acidic condition. Samples were tested directly after curing in a water bath. Second, the 45-day acidic condition. 1/3 of the samples were tested after 45 days of immersion in acid. Third, the 90-day acidic condition. Another third of the samples were tested after 90 days of immersion in acid. Figures show the samples for each condition. There is the non-acidic sample, the 45-day acidic sample, and the 90-day acidic sample. Tests conducted: the following tests were done on both fresh and hardened concrete. Compressive strength, indirect tensile strength, impact resistance, dimensional changes, volumetric electrical resistance. Chapter 4: Analysis of experimental results. We begin with compressive strength under non-acidic conditions. When microsilica is used alone, higher microsilica content leads to greater increases in compressive strength. Fibers alone did not have a significant effect, but the combination of microsilica and fibers slightly improved the strength and showed good synergy. Under the 45-day acidic condition, a degradation mechanism occurred. Hydrogen ions attacked the concrete and reacted with calcium hydroxide present in the mix, producing gypsum and ettringite. These secondary products are bulky and reduce the compressive strength. The results showed that higher microsilica content reduced strength stability, while higher fiber content improved compressive strength retention. Therefore, using both microsilica and fibers simultaneously, high fiber content with a moderate amount of microsilica can create a relative synergistic effect. Microsilica increases cement paste density, while Forta-Ferro fibers control cracks and prevent acid penetration. For the 90-day acidic condition, the same mechanism occurred, but the chemical attack was more severe. The results were almost similar to the 45-day case. The final conclusion was that combined samples with the highest fiber content performed the best. Microsilica can be used at 7.5% or even 15%, but the fiber content should be maximized. A comprehensive analysis of the samples was performed, and a predictive model was developed. The compressive strength of the reference sample under non-acidic conditions was considered as a baseline. Model parameters included the number of days of acid immersion, the weight percentage of microsilica, and the volumetric percentage of Forta-Ferro fibers. The predictive model showed good accuracy. Comparative charts between experimental results and the model, as well as response surface plots, were provided. For the indirect tensile strength test, 3 factors were influential: the quality of the cement paste microstructure, the bond in the transition zone and stress distribution, and crack control. Under non-acidic conditions, fibers had a positive effect, and the best performance was observed in the combined samples. Under the 45-day acidic condition, the same degradation mechanism occurred, and once again, the combined samples performed best, especially when 0.4% fibers were used. In the 90-day acidic condition, samples containing only Forta-Ferro fibers showed only a 1.9% reduction in strength compared to the non-acidic condition, indicating stable performance. Combined samples with the highest fiber and microsilica content also exhibited effective synergy, with a strength reduction of approximately 22%, performing better than the reference sample. This slide presents the results of the indirect tensile strength test. Samples containing only microsilica, only Forta-Ferro fibers, and the combined samples are all shown in the chart. The graph illustrates the overall trend of tensile strength variations under the three different test conditions. An analytical evaluation was also performed for tensile strength, and an analytical relationship was developed. The comparative graph of experimental data and the model shows good agreement. Response surface plots are provided for the 0-day, 45-day, and 90-day conditions. FT represents the tensile strength of the samples, and FTR indicates the tensile strength of the reference sample under non-acidic conditions. We now turn to impact resistance. For impact resistance, two criteria are important. First, the energy absorbed up to the first crack, which indicates the onset of damage, and second, the energy absorbed until complete failure, which represents the toughness of the sample. Under non-acidic conditions, the results showed that adding microsilica alone makes the concrete more brittle and reduces impact resistance. The higher the Forta-Ferro fiber content alone, the greater the impact resistance. With 0.8% fibers, the maximum resistance was observed. Samples containing 0.8% fibers combined with 1% microsilica showed acceptable performance. In the 45-day acidic condition, samples with 0.8% fibers again showed the best performance, and the combined samples performed significantly better than the reference sample. In the 90-day acidic environment, using microsilica alone caused a severe reduction in resistance. Forta-Ferro fibers provided the highest impact resistance. Combined samples with a high microsilica content, such as 15%, experienced a considerable drop in resistance compared to the 45-day condition. Therefore, the optimal approach for impact resistance is to use a high proportion of Forta-Ferro fibers or a combination of 7.5% microsilica with a high fiber content. We now move on to visual deformation and durability. In this experiment, three parameters were examined: weight loss, reduction in diameter, and reduction in height. Regarding the effect of microsilica without fibers, under non-acidic conditions, replacing part of the cement with microsilica caused the samples to have slightly lower weight compared to the reference sample. Under acidic conditions, the higher the microsilica content, the greater the loss of weight and diameter. In contrast, increasing the fiber content reduces weight and diameter loss, as the fibers help distribute stress and prevent the propagation of microcracks. When microsilica and Forta-Ferro fibers are used in combination, the performance is moderate and relatively stable, provided that excessive microsilica is not used. Overuse of microsilica can lead to brittleness and make the concrete sample more vulnerable to damage. We now turn to the volumetric electrical resistivity test. This test was conducted to evaluate the durability and permeability of concrete. When examining the effect of microsilica without fibers, under non-acidic conditions, increased concrete densification led to higher electrical resistivity. However, under acidic conditions, increasing the microsilica content caused a relative decrease in resistivity compared to the reference sample. When analyzing the effect of fibers without microsilica, the fibers had little impact on volumetric electrical resistivity, and at higher percentages, the resistivity even decreased compared to the reference sample. Nevertheless, over the 90-day period, the relative resistivity was better maintained because the fibers blocked penetration paths and prevented acid from entering the concrete. The combined effect of microsilica and fibers showed that using an optimal ratio, 0.4% fibers and 7.5% microsilica, reduces permeability and increases resistivity. The predictive model showed good agreement with the experimental results, and response surface diagrams were provided for 0-day, 45-day, and 90-day conditions. The reference sample is the one without any additives. Finally, we reach the last chapter, results and recommendations. In this section, to summarize the findings briefly, the presence of microsilica alone under acidic conditions does not have a positive effect on compressive strength and can even lead to further reduction. On the other hand, when only fibers are present, the compressive strength remains relatively stable, showing the least relative reduction among all mixtures. However, when both additives are used simultaneously, samples with the highest fiber content along with a certain amount of microsilica, up to 15%, exhibited excellent performance in terms of both compressive strength and strength stability after 90 days in an acidic environment, compared to the reference sample. For the indirect tensile strength test, similar results were observed. Fibers helped maintain the strength, while adding microsilica improved the concrete's microstructure, resulting in desirable tensile strength for the concrete samples. Regarding the impact test, it was found that fibers increased impact resistance, whereas microsilica caused brittleness and reduced resistance. Additionally, the energy required to initiate the first crack and to reach complete failure decreased significantly with microsilica, making the samples more brittle. In terms of visual deformation, the trend was similar. Using microsilica alone under acidic conditions reduced performance relative to the reference, while fibers without microsilica provided better long-term performance, resulting in the smallest reductions in weight, diameter, and height. Regarding volumetric electrical resistivity, under non-acidic conditions, using microsilica alone increased resistivity 3 to 4.5 times compared to the reference sample. Fibers alone did not have a significant effect, but when combined with microsilica, they helped maintain resistivity over the long term and greatly improved electrical stability compared to the reference. Finally, theoretical models were developed for all three tests. The results obtained from these models showed very good accuracy when compared with experimental data, and there was excellent agreement between model predictions and laboratory results, confirming the validity of the proposed models. These are also recommendations for future research. In conclusion, I sincerely thank you for your patience and the attention you have given to this presentation.